Okay, so let's take a closer look at the numerical patterns of functions that we talked about before. You know that from experience, it's actually much easier to identify the type of a function given its formula or its graph than a list of numbers that, you know, it comes from some kind of situation or someone just made up, and you have to go, okay, do these numbers fit a linear or quadratic, etc. function? And unfortunately, that's really what we actually will be doing most often, and by which I mean that's actually the most useful skill, because usually, you don't get a formula. When you do a scientific experiment, for example, you get a list of numbers. And one of our goals in pre-calculus and as mathematicians is to be able to figure out how you can write an equation to model a list of numbers that you're given so you can extract more data in between those numbers or extrapolate and figure out and make predictions about that list of numbers or that situation. Anyway, here I have the four types of functions you looked at. In fact, let me scroll down a little to get all five types of functions you've looked at by this point: linear, quadratic, power, exponential, and logarithmic. And in blue, I wrote down the general formulas: y equals mx plus b, y equals ax squared plus bx plus c. The power function, remember, in the is x in the base, so it's y equals ax to the b. Exponential is x in the exponent, y equals ab to the x. And the new type of logarithmic function, the logarithmic function, y equals a plus b log base c of x. So here we have some kind of y-intercept a, and we'll take a look at why we have that here and not necessarily in the other functions in terms of the general formula in a moment. Um, just beware that, we say log base c of x. Usually we just stick with either log base 10 or ln, because as you know, we have this thing called a base change formula, so it doesn't actually matter which base we use. And because it's easiest to do calculations in base 10 and base e, we use those instead. In purple, I wrote down the numerical patterns of these functions. We have the add, constant second difference, multiply, multiply, add, multiply, and the new one, which is multiply, add. So let's go over these numerical patterns with some examples, and then I'll talk about what multiply, add actually means. Okay, so I have a table here. On the very far left side, I have a whole bunch of x values, 1 to 6. And then I have 5 functions. And I can tell you right now that these functions are in order, linear, quadratic, etc., like the table just above this that you can't see anymore because I just scrolled down. Anyway, if you look at f of x, the linear function, right? Remember when we say add, we mean that if we add 1 or on with the x value, over here we add -4, or we subtract 4, and if we just keep adding 1 over here on the left, oops, that's not a 1. There we go. We add or subtract the exact same value. So what that means practically is that if you move along the x-axis at a certain pace, right, one step at a time, you move along the y-axis, the y values go up or down at a constant rate at a constant pace, which we call the slope in the linear function. Every time we move one step to the right, we move 4 steps down in this function in terms of the y-axis. With the exponential, since we're talking about add blank, with the exponential, instead of going down by, a constant rate, we actually go up or down by a constant multiple. So here, every time I add 1, I'm going times 2. I'm doubling my y value. I could triple, right? If my base was 3, if it was 3 to the x, I would triple. if it was if the base was a fraction between 0 and 1, I would maybe half, or I don't know, third. I don't think that's a verb, but you go up or down, you add or you multiply or divide by the same number every time you go up a certain step with the x. And this also works if you go like plus 2, right? If you go from 1 to 3, then I'll undo that so I I can draw on it in another color later. If I go from 1 to 3, with f of x with the linear function, I'm going minus 8. And 3 to 5, I'm going plus 2. 4 to minus 4, I'm going minus 8. Same thing with the exponential. If I go 2 in x plus 2 in x, I go times 4 in p of x. And so I could actually skip steps as long as my steps are evenly spaced. I have the same kind of up or down motion, either plus or minus or times or divide in the function, in the y value, depending on whether it's linear or exponential. With the quadratic function is a little different. We saw that if we actually looked at the differences, we get plus 1, plus 3, plus 5, or some kind of arithmetic sequence, or a linear function, if you will. So what that means is that every time we go up a step in x, the y, or the function g of x, goes up or down by a different amount, but that different amount's very predictable, in that that different amount is actually an arithmetic sequence or a linear function in itself. So if we look at the second difference, so if we say, okay, we take this plus 3 and this plus 1, and we look at what's between them, we get a plus 2. And same here, between plus 3 and plus 5 is plus 2. And if you look at 14 to 21, that's plus 7. And going from plus 5 to plus 7 is another plus 2. So remember, we said that what this means is that the rate that y is changing is not always the same, but the rate at which the rate changes is constant. Right? So you're not going up always at the same speed, but that speed is predictable and changing at a constant pace. Another way of saying this, thinking about this, is if you remember in physics, right, you have this thing called velocity, which is how fast your position is changing, how fast you're moving, and then you have this, what we call second order rate with acceleration, which is how fast your speed, your velocity is changing. So a quadratic is like that, in the sense that you have the rate, sort of the speed the function changes is variable, but the rate at which the rate changes, the speed of the speed, if you will, is constant and at a plus 2, which also relates to, if you remember from physics, if you throw an object up, it with only gravity acting on it, it makes sort of a parabolic arc, right? There's of course a relation with this, in that there's the constant acceleration from the gravity, and here we have the constant second order difference, which is the rate of the rate, just like acceleration in physics. Anyway, let's talk about the multiply, 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 add properties. Those are actually the hardest ones to spot, because if you notice in Q of x, well, I didn't actually put in all the numbers, because one thing is you don't actually need all the values from 1 to 6, from x equals 1 to x equals 6, to actually spot the pattern. And also, as we'll see later, some of these numbers are actually really hard to get. It's more natural to only have a subset from 1 to 6. Let's look at h of x, and I'll switch colors so we can actually see more clearly. From going from 1 to 2 in x, I'm multiplying by 2. I'm also adding 1, but let's think about this as multiplication now. And the next time I multiply by 2 is from 2 to 4. So x equals 1, 2, and 4 are the ones we're going to focus on right now. In h of x, notice that over here from 3 to 12, I'm multiplying by 4. And from 12 to 48, I'm multiplying by 4 as well. So that's what we mean by multiply. Every time we go up by a multiple in x, we go up by a multiple in y, or h of x, or the power function. If we go from 3 to 6, we're also multiplying by 2, which means that 27 to 108, that actually should also be times 4. And that's actually true. If you divide 108 by 27, you get 4. Or multiply 27 by 4, you get 108. 5, because it's a prime number and it's not a multiple of anything before that, we don't really see the pattern here. So you actually kind of need to get up to x equals 10 before you can see a pattern with 5. So that's one reason why multiply whatever patterns are hard to spot. It's that some of these numbers actually don't do anything in terms of helping you to spot that pattern. Okay, q of x, that's a logarithmic function. Notice that going from x from 1 to 2, I multiply by 2. But here, I'm also multiplying by 2. 10 to 20. That is totally true, so it could get confusing, and it does happen quite often. But right now, I'm actually looking at a difference, which is plus 10, and you're like, but wait a second, it could be times 2, like, why are you doing plus 10? Because, well, if you look at x equals 2 to x equals 4, that's not the same ratio as going from x equals 1 to 2. If we look at this as a multiplication, if we think of this as a power function, multiply, we go, oh, 10 to 20, that's times 2, then q of 4 should be 40, because 20 times 2 is 40. It isn't. But here in this list of numbers, the differences are what's constant. So that's what we mean by multiply, add. Every time we multiply the x value by a certain factor, in q of x in the function, in the logarithmic function, we go up by a constant number of steps. So in some sense, it's kind of, well, the logarithms are the opposites of exponents, right? So it makes sense, I guess, that this is sort of the opposite pattern of the exponential function. Exponential, we have add, multiply. Logarithmic, we have multiply, add. Okay, so before we go on to the last thing, let's figure out what the other numbers in q of x are. So this is actually, I didn't put in those numbers because those numbers actually don't really fit in that table. We know that when x is equal to 1, y is equal to 10, and we know that when x is equal to 2, y is equal to 20. And y is, what did I call it again? Q of x. Right, y is q of x. And we've already identified that this is logarithmic, which means the formula looks like y equals a plus b log x. Notice that, as I said before, I'm not just going to use log base 10. That's going to actually make my life a lot easier, because if I didn't know what base it was, I have 3 variables. So remember, like when you had a quadratic and you have 3 variables in order to fit a quadratic through some points, it took a lot longer than just solving for 2 variables in, say, a linear equation, or in finding a linear equation. So I'm going to just eliminate the base to make this a little simpler. I gave you, or you were given, I was given x equals 4, but we don't actually need it because we only have a and b to solve at this point. So we only really need 2 points. I could have used 2 and 4 or 1 and 4, but smaller numbers make the math easier. So why don't we just use the smaller numbers? Okay, so just like fitting points into any other function, once I know what type of function I'm dealing with and can write down a formula and know a few points, I can start plugging the points in. So let's do the first one. 10 equals a plus b log 1. And the second one is 20 equals a plus b log 2. And remember, our goal here is to find a and b, and therefore finding the function. Okay, there's actually another reason why I used x equals 1, because if you remember, the log of 1 in any base is equal to 0. Right? That's the x-intercept of any log base, whatever x equals y equals f of x. So if I use x equals 1, that's kind of like the y-intercept, because, well, it is an intercept, it's an x-intercept, right? Of logarithmic functions. Logarithmic functions have no y-intercepts, but they have x-intercepts, so that's kind of the easy point. Like in linear functions, the y-intercept's the easy point that you plug in. In a logarithmic function, the x-intercept, x equals 1, is always the easiest point to deal with. If we look at the first function, oh sorry, the first equation, well, log 1 is 0, so this entire term goes away. A equals 10. Boom. It's like we already have half the problem done. We don't need to do any like crazy elimination stuff like we do in quadratic functions. We do have to substitute, but that's easy. We know a equals 10, we can plug it in here. So 20 equals 10 plus b log 2. That means 10 equals b log 2. B would be 10 divided by log 2. And if you use a calculator, because, well, unless you memorize log 2, it's pretty hard to figure out what this is in decimals or in any more accuracy than 10, or in any more useful way than 10 over log 2. This is about 10 over 0.3. So let me change this to about. And that would be about 33.3. And so the function we're looking at is q of x equals a is 10 plus what was that? 33.3 log base 10, so I don't need to write the base of x. And as you can imagine, putting in numbers like x equals 3 or 7 or 5 in here would just make it really bad. Right? It just happens to work out really nicely with log of 2 and log of 4, because this function in some sense was constructed to fit data that was really nice at those points. And usually when you have logarithmic data, when you have data that fits a logarithmic function, you know, what you actually end up having values of are the nice ones. It's not like, I'm giving you the nice ones because I love you and don't want you to do really hard math. It's that really practically, those are the points that you actually would observe, or those are the points that would be given in those are the points that would be given in the context, whichever context it is. Speaking of context, so there's always the question, why are we doing this? What are all these things good for? So we have 5 kinds of functions. Linear, we already said, it's something that has a constant rate of change, a constant slope. And linear functions, you've already studied them pretty much to death since you were in Algebra 1 or even before that, right? So we know that linear functions can be used to model things that go up or down at a constant rate. You earn $5 a day, you eat 2 apples a day, or whatever. Anything like that, linear function. Quadratic, we know, has a constant second order difference or second difference. And you know that quadratics can be used to model, say, the flight path of a beach ball. If you toss it up in the air or you toss a volleyball up in the air, you get a parabolic shape. And by the way, that's why there's a volleyball player on the cover of your Algebra 2 book, because Algebra 2 has like a ton of parabolas in them, and volleyballs make parabolas. Hooray! And you know that quadratic functions, you can there are times, like, I don't know if you remember, but say if you have a box, right, and you're trying to make a box from folding up a piece of paper with corners cut out. The corners are X or whatever, and this thing's 11 by 17 in original size, something like that. because when you multiply these terms out, like 17 minus 2x, this would be 17 minus 2x, this would be 11 minus 2x. If you multiply the width and height of this box out, sorry, the width and length of this box out, you'll get x squares. You also end up getting a quadratic. So quadratic functions can be used to model some kinds of area problems. Power functions are functions that go up by a constant multiple, but only when x goes up by a multiple. So in some sense, it's actually harder to think of how a power function goes up or down as a rate of change, because when we say rate of change, we look at evenly spaced x's. X equals 2, x equals 4, x equals 6, x equals 8, etc., etc., etc. But in a power function, we're looking at something like x equals 2, x equals 4, x equals 8, we skip 6, x equals 16, and so on. And one thing that you already know that power functions can model really well is areas and volumes, right? For example, if I look at a square with a side x, its area is of course x squared. If I look at a circle with a radius r, the area is pi r squared, which is a power function. It's also a quadratic function, but because we don't have any plus bx plus c, we can think of it, or it's easier to think of it as a power function to categorize it with all these other simpler area problems and these volume problems, like x cubed is the volume of a cube. Further, it's pi r cubed from one of the problems you did in one of the previous assignments is the volume of a sphere. Either pi what was that? 4 pi r squared. Yes, that's the surface area of a sphere. That's what I meant to say, sphere. I almost said cylinder. Right? So all these things are power functions, and one of the things that you may have encountered or thought about before is, hey, remember, if x gets doubled in a cube, if the side gets doubled, you don't actually double the volume. The volume, or the y, becomes 8 times the volume. So that's the multiply property. Every time you double the width of this cube, you octuple, I guess that's the verb. You octuple the volume, you multiply the volume by 8. And if you had a square, you would sorry, not double, but quadruple the area. Multiply, multiply. Exponential. So exponential functions. This is one, this, let me write this down first. Goes up by a constant multiple every step. So what this also means is that constant multiple, remember this is a multiple of the previous number, so like in a geometric sequence, you multiply the previous number by, like, I don't know, 10 or 0.5 or whatever to get the next number. We can also think of this as a constant percentage or ratio or whatever other word that means fraction, right? If we're doubling, we can say we're increasing by 100%. We're getting 200% of the previous number every time. Or if we're halving, we say we have 50% of the previous number every time. There are, of course, way more complicated things, like we go every time we multiply by 1.03, which means it increases by 3%. So an exponential function models things that increase by a constant multiple or percentage of the previous number at every step. And we talked about populations. If I lock 10,000 bunnies in a room and have them breed with each other, there's gonna be a whole bunch of bunnies in like a couple of months. But if I only lock 50 bunnies in a room, there'll still be more bunnies. It's just that because 50 is a lot less than 10,000, a lot smaller than 10,000, I'm going to get a lot fewer baby bunnies. And we can say that the number of baby bunnies is a certain percentage of the number of adult bunnies if we assume that every pair of bunny breeds and every time they breed they produce two new bunnies. We can actually say that the bunny population increases by 100%. Of course, that doesn't account bunnies dying, but let's not worry about that because bunnies dying is kind of depressing. We'll deal with that later. Um, You also looked at things like bacteria, which are less adorable than bunnies, but they still go up by a certain percentage or down by a certain percentage if you have bacteria in your body and you're taking antibiotics at every constant interval of time. And of course, there's the financial one, which is if you put money in a bank or you take out a loan, you're charged a constant percentage of interest every month, year, day, whatever it is, whatever the terms of that loan or savings account is. Okay, logarithmic functions. This is going up or down by a constant amount every time x is multiplied or goes up by a factor, by a constant factor. So in the previous example, we said we double. Okay. One of the things that you observed in an exponential function is that an exponential function goes up really fast, right? Every step you take, you triple or quadruple or whatever it is, your y value. The logarithmic functions, you saw the graphs already, are and just from the algebra, they're complete opposites of exponential functions. Instead of saying every time you take one step on the x, you go up by a whole bunch in the y, what we're saying here is every time you multiply x by something, every time you go up like a whole bunch in the x, your y only goes up a constant amount, which could usually is small relative to the x. So for example, in this g of x, you can imagine, since this pattern keeps holding, you can imagine, well, okay, if I'm going from 27 million to 54 million in x, right? That's a lot of x's. But I'm still only doubling x. I shouldn't say still, that's a lot of x's. But y only goes up by 10. So even though x goes from 27 million to 54 million, y goes up by 10. It's not very much. Logarithmic functions are extremely, 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 extremely slow. Now, there's no asymptote still. It doesn't stop. So it keeps going. It's just really, 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 really slow. And it gets slower and slower and slower. Because if you go up to like 27 trillion, it's going to take another 27 trillion in x to get q of x to go up another 10. Which you're like, okay, that's like the craziest function ever. Why do we want that? It's kind of dumb. Well, one example that you may have already looked at is actually, well, sometimes we want to make something logarithmic on purpose. So for example, we have the Richter scale for earthquakes, and we said that, and in the example that you may have looked at, I don't know if you actually got to that yet, if we had a 1,000 ton quote unquote explosion, as in it's 1,000 tons of TNT worth of energy, the Richter scale magnitude is only 4.0. While if we look at a 1 million ton one, it's only 6.0. So if you look at this, well, then you know that this is a logarithm, right? The 4 tells you how many, kind of, not really, it tells you how many zeros, how many places you have in the x value. And also, if you look at it, you go up by, I don't know how many times is this, a whole many times on the x, you only go up by 2 on the y. So if you imagine going up by the same factor, let's see, so that's adding 3 zeros. So if I go to 1 billion tons, you're only going to get up to an 8.0 in the Richter scale. Which you go, okay, that's not super useful, because why don't we just say 1 billion ton? Well, first of all, saying 1 billion ton is kind of annoying. 8 is a little easier, but then that's just me being lazy. Also, if you look at the actual Richter scale and like what people would do when they hear the news, a 4 is, you know, it's bad, but it's not too bad compared to an 8. In fact, an 8 is much, 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 much worse than a 4. And every time you go up a step on this Richter scale, on this logarithmic scale, because of the multiply add property, every time you add in the y, you're multiplying in the x. That your y value determines what we call the order of magnitude, or essentially the severity of the actual explosion, the actual earthquake in the X. And because earthquakes, well, they suck and they go up really, really, really high in terms of um energy release, equivalent to tons of TNT, which I guess we're obsessed with because we like explosives. I don't know. I guess it's just a good way of measuring destruction. Well, it gets really bad. There are 9.0 earthquakes happening, not all the time, but often enough that we want we want to make sure that we have a way of denoting them in terms of magnitude relative to the smaller ones. The 1.0s, the 2.0s, those we don't actually really worry about. Practically, in terms of, if you live in an earthquake area, knowing the Richter scale magnitude gives you a better sense of how to prepare for things. If you hear a 1.0, oh, it's you mentally say it's a very small earthquake. I may feel a little bit, but that's about it. But if you hear a 6.0, then a million tons of TNT. That sounds like, okay, like that's very abstract. But if we say, okay, it's on a scale of 6 in terms of severity, well, what does that do? It brings down houses. And on a scale of 8, it brings down pretty much everything. While on a scale of 4, it doesn't bring down very many things, etc. And this logarithmic scale is essentially manufactured so that we can interpret these large numbers. Most of the time, a logarithmic function, at least logarithmic functions that we'll be looking at, most of the time they're actually manufactured so that we don't have to deal with very large numbers. Just like how logarithms were first used so we can do calculations with logarithms instead of very large numbers. Here, logarithmic functions are used so that we can look at very large numbers and make sense of them. So, in I guess going back to this whole why are we using logarithmic functions, one reason is that it's actually really useful in terms of simplifying data. Of course, there are functions that are naturally logarithmic, and we'll encounter some of them later. For example, I'll just give you a quick example. If we look at, let me draw a picture. Right, I have water and I have the sun. If you look at the intensity of sunlight underwater, you can, like right here at the surface of the water, there's a lot, assuming there are no clouds, there's a lot of sunlight. But as you go deeper, every step that you go, light's going to be dimmer. In fact, the way that it works is that every, say, 1 meter you go, the amount of light you get is going to be a fraction, a portion, a multiple of the amount of light from 1 meter above it. So this is, if the x is a depth, every time x goes plus 1, y, which is the amount of light, y goes, maybe 1/2 or 1/3. We'll look at a very specific example in the future, but no matter what this multiple is, this is an add multiply or add divide, if you want to call it that way, pattern, and so this is actually a logarithmic function. And this is one that's not manufactured. It does happen. Take a flashlight and a tub of water and a light sensing meter thingy. I think I have one of them, but I don't know if it's waterproof. And give it a shot. Or just, go under the puddle in the freezing ice.